Nice to meet you. I'm Prof.Joun working for GNU in Korea. The topic of this lecture is approximate method of boundary value problems and concept of FEM, especially for the beginners. Some more detailed contents can be found from this reference, which is targeted at introducing finite method coupled with mathematics and solid mechanics. First, we are going to study functional with a boundary value problem of a cantilever beam. In solid mechanics, strain energy is defined by this equation in terms of bending moment or deflection curve. For example, assuming length L equals 1, fractional rigidity EI equals 1, and load intensity function Qx equals -2 for this cantilever beam, so we can obtain B double prime x and MBx equals -x squared plus 2 times x minus 1. Boundary conditions B0 and B prime 0 are all zeros. Solutions of this boundary value problem equals this function. Because we are interested in approximate solutions, we attach it, a star mark, as a superscript for an exact solution like this. To the contrary, tilde mark is employed to emphasizing the approximate solution like this. When we plug this function to the functional, that is a definite integral of input function, we can get a real value of 1 over 10. So we can conclude that the input of the functional is function and its output is a real value. You know that both the input and output of a real value function are all real numbers. Therefore, functional is sometimes called functional function. Anyway, I want to emphasize that we have stayed near the functional for a long time, and I hope you to pretend all friends of the functional. Now I am going to introduce a very important theorem in solid mechanics, that is minimum total potential theorem. This theorem indicates that the material or structural system experiences elastic deformation to minimize the total potential, which is a function of function that is functional, defined for a material or a structural system. It is theoretically based on Birchwork principle. Even though you are not familiar with this principle at this moment, you'd better accept the minimum total potential theorem as you live without any knowledge about the birth or origin of the human being. Anyway, using the same conditions, we can derive this functional, which should be minimized with essential boundary conditions satisfied. The problem composed of functional with essential boundary conditions is called variational principle. Okay, to look over the forest before finding best place for dwelling, I will introduce a procedure of obtaining an approximate solution from this variation principle. First, we can sum the approximate solution by tilde like this as a linear combination of non-functions, x squared, x cubed, and x to the 4th, which meet the essential boundary conditions. And now we have to plug this trial function into the functional to obtain a new function of C1 and C2 and C3. The functional reduced to just a function. Still, we did not apply the minimization. we'd better recall what we have done. The most innovative change is that the problem of minimizing a functional in infinite dimensional function space was simplified by a extremizing problem of function in finite dimensional vector space, in this case, three-dimensional vector space. When we apply the necessary condition to get the minimum point, in this case, partial differentiation of the new function with respect to three unknown constants give us three linear equations. From these equations, we can calculate the unknown constant like this. After plugging this constant into the tilde function, by tilde, we obtain the solution that is exact. Yeah, it should be like exact. When the trie function can describe the exact solution, then we have to obtain theoretically the exact solution from the Bayes principle. This is theory. Of course, theory is reality. Okay, let's solve another beam example to get approximate solution from Bayes principle. This figure is a very special beam deflection problem made by myself about 2 decades ago. It is very special in terms of boundary condition, that is shear force and slope at the left end and displacement and bending moment at the right end are all zeros. We assume that the length L equals 1, W0 equals 2, and fractional rigidity equals 1. Then the boundary barrier problem is summarized like this, and its corresponding Bayes principle can be stated like this. It is very interesting to note that the natural boundary condition disappeared in this Bayes principle. It's very curious. Yeah. However, at this moment, if you have never studied on analytical mechanics, you may have some difficulty in recognizing or accepting this fact. Anyway, this situation tells us that we can meet both the governing equation and natural boundary conditions by minimizing this functional. Almost 110 years ago, when there had been no computer and solid mechanics had never been much advanced, a pioneer, Rich, he suggested an approximate approach of solving the boundary barrier problems from Bayes principle with approximate trial functions which meets only the essential boundary conditions. Now, following his way, we will try to get approximate solution starting from these three trial functions. You know, the exact solution is a fourth order polynomial, but three trial functions are linear, quadratic, or cubic functions respectively. So we can obtain the exact solution at all in this case. Okay, now we have to plug these functions in this functional to fold the problem down from heaven to earth. That is from infinite dimensional function space that can be handled by God to finite dimensional function space that can be handled by human being. Okay, I will show you some details to reach the final goal with trial function 3. Plugging this trial function to the functional, we can get a two-dimensional function like this. From the necessary condition for this function to be extremum, a set of these two linear equations is obtained, and we can find the final approximate solution as stated here. This figure compares approximations with the exact solution, implying that even the linear approximation can be meaningful. Please think something out of this figure because it involves much more value than what you can imagine at this moment. Now let's tackle the core of this method based on our common understanding about the extremization of a function. When a function to be extremized is given, we are used to applying the necessary condition first to solve the extremum or inflection points. For example, to extremize this function, we have to solve this necessary condition to obtain the potential extremum points. Now, let's consider the reverse of this process, the above process. Let's assume that we can obtain the function associated with the given equation by integrating it, which is the necessary condition of this function. Then a new virtual problem to find stationary points, including extremum or inflection points, is equivalent to its model equation. Of course, to find the solution of the virtual problem is more algebraically difficult in most cases, as far as we know. So this reverse process is not practical, of course, in algebra. Anyway, we'd better think that the process is right, regardless of the practicability for the simple cases. If we cannot get the solution of the equations by hand calculations, and there is a very powerful tool to approximate the extremum points for their corresponding functions, then the reverse process can be beneficial. Unfortunately, I don't know if there are some cases of extremizing functions instead of solving their associated algebraic equations. At any rate, especially in case of solving a differential equation of which exact solution cannot be found, the reverse process is inevitable for approximation. For example, solving this boundary value problem is exactly equal to solving this variation principle. It will be verified in the next slide soon. Consider the case that we cannot obtain the solution of the boundary value problem, then there is no way to obtain an approximate solution from this strong form of the boundary value problem. It's so strong. Strength is good, but it sometimes generates big problem, That's the way it goes. However, this is a weaker form corresponding to the boundary value problem. Yes, it looks weaker because it involves less order of derivative than the strong form. So it gives us some good idea for approximation. Of course, we already experienced the approximation. From these graphics of function set, let's explain the idea of the approximation. According to this variation principle, there is a function minimizing this functional inside this function set, which satisfies the essential boundary conditions. We'll get to know soon this red one is the function we want to find. Even though we cannot approach to the exact solution, that is a point in space, we can try to get closer and closer to the point where the exact solution is waiting for us. And we can get some approximate solutions. Of course, the accuracy can be enhanced if we know well about the problem and some related techniques. That's why we are studying. Now let's derive the Euler-Lagrange equation corresponding to this Bayesian principle. Assume that pi star in this physical function set which satisfies essential boundary conditions minimizes this functional, and phi tilde is a function in the same physical function set. Let's put the pi tilde like this. That is pi star plus epsilon times eta x. Then we assume epsilon is an arbitrary constant and eta x is an arbitrary function. Of course, the phi tilde should meet the essential bound conditions. So eta 0 and eta 1 should be 0. It is because the same values exist on both sides at any point x equals a where essential boundary condition is imposed, as can be seen in this equation. They should be balanced, and there is no way but eta a should be 0 because epsilon is arbitrary. It should be emphasized that phi tilde involves all functions inside this function set, a physical function set, because of arbitrary constant epsilon and arbitrary function eta x. The constraint imposed on eta x is aimed to make it stay inside this physical function set. To check local extremization around the fixed function pi star, we conduct this simple arithmetic calculation to get this relationship. We can state if the first term on left side vanishes, then a pi star becomes locally minimum. And because the second term on the right side is always non-negative. Because epsilon is arbitrary, this term should be 0 to make phi star minimize the functional. Applying integration by parts to this equation, we obtain this equation after plugging the constraint on eta x at the boundaries in this equation. Because eta x is arbitrary, this differentiation should be satisfied. This differentiation is called Euler-Lagrange equation. It's very, very, very important. This differentiation with the boundary conditions is called the boundary value problem corresponding to this Bayesian principle. Of course, the pi star is stated here. You can find it by yourself. Okay, now let's proceed towards this method with strength because we are now armed with theoretical backgrounds. That is, we verify that the Bayesian principle is the same with its corresponding boundary problem when there exists the only solution, and that is the unique solution. Now we are about to link mathematics with engineering problems. And this is a one-dimensional steady-state heat conduction problem. Now assume that K equals 1 and heat generation per length Q equals x squared. At both the ends, the temperature are maintained 0. Then equation of heat conduction can be reduced to this boundary value problem. Of course, its exact solution can be easily found like this. after integrating both sides twice and imposing boundary conditions. You know that this variation principle is equivalent to this boundary value problem. From this boundary value problem, we cannot generate any idea for approximate solution at all. However, following this method, we can get approximate solutions from this variation principle. Of course, I think you know that this idea is the major theoretical background of FEM we want to study further. Now let me introduce you how to obtain approximate solution in this method. It starts from variation principle with an assumed approximate solution called trifunction, which is a linear combination of known functions called basis functions. In this case, two basis functions x 1 minus x and x squared 1 minus x are employed. Of course, the trifunction should meet the essential boundary conditions. Let's start with this trifunction. When we plug x equals 0 or x equals 1 in this trifunction, the function values are all zeros. So it meets the basic requirement on essential boundary conditions. After simple arithmetic treatment, we obtain this two-dimensional function of C1 and C2. Applying the necessary condition for this function to become extremum, we obtain two equations in this matrix form. We can see that the matrix is symmetric. It's very important. Solving these linear equations and plugging the constant in the trifunction, we can get the approximate solution of a cubic function. Of course, the exact solution is a quartic function. Now, let's check the accuracy of the approximate solution. This figure compares the approximate solution with the exact solution. I used the solid line for approximate solution on purpose because it is much more important than the exact solution from now on. Even though the exact solution is a quartic function, while the approximate solution is a cubic function, they are very similar in the region of interest. The maximum error in terms of temperature or function value is around 2%, even though we employ only two known functions, that is basic functions, in this method. The reason of good quality lies in that the quality of basis functions employed is quite good in terms of solution accuracy for this case. However, it is also interesting that the slope error cannot be neglected. It is one of the characteristics of approximate solutions, which can be overcome by increased number of basis functions with better quality in terms of solution accuracy. Now, according to the related theories, basis function for a trifunction should belong to pth order Sobolev function space, when the differentiation is 2 times p order to guarantee the solution compatibility. It is very interesting that the solution accuracy analysis when basis function is additionally added, implying that the approximate solution eventually converges to exact solution when the trifunction employs infinite number of basis functions. This discussion is very important for FEM, which is supported by computer. With assistance of computer, FEM dares to use geometrically very bad basis functions, that is interpolation functions, because computer pushes FEM to go straight without showing backside. Believe me. There are two ways of solving boundary problems. Up to now, we have studied one of them, that is the Bayesian approach represented by this method for approximation of the boundary problems. Now we are going to study the second one, that is weighted ledger method with emphasis on collecting approximation, which is more general of the two. It starts directly from the boundary value problem. This is the same boundary problem identified by problem 1 with that employed for this method. We can obtain this expression identified by problem 2 after multiplying both sides by weighting function omega x and applying integration over the line segment of interest. Of course, if the problem 1 is true, then the problem 2 always becomes true. However, its inverse is not satisfied. When we assume that omega x is arbitrary, then the problem 2 should be identical with problem 1. Now we apply the rule of integration by parts onto the first term of the problem 2 to reduce the maximum order of differentiation in the problem formulation. This is the result. Now let's assume that weighting function omega x at x equals 0 and 1 equals 0 because essential boundary conditions are imposed at the points. If you understand the constraint imposed on the eta function in this method at the points where essential boundary conditions are given, you can accept this assumption without any hesitation. Now, we obtain weak form as summarized here. So the problem can be stated that the solution function belonging to the feasible function set should meet the weak form for any function belonging to the weighting function set of which element should have zero function values along the boundaries where essential boundary conditions are imposed. It is a little imaginary and quite ambiguous. So we better try to come closer to the essence of the approach by solving example. Gherkin suggested that the trial function is the same as that of this method, and that the weighting function employs the same basis function used for the known functions to obtain an approximate solution. For example, we have to approximate both unknown functions and weighting function using the same basis functions of x or 1 minus x and x squared 1 minus x, as can be seen in these equations. Here, C1 and C2 are unknown constant, and W1 and W2 are arbitrary constant. Of course, it can be easily checked that two functions satisfy their associated requirements. Inserting these of two functions into the weak form, we can derive an identity equation. Of course, we have to rearrange the equation with respect to arbitrary constant like this, because the coefficient of W1 and W2 should be 0. Therefore, we obtain two equations, which are written in matrix form like this. These linear equations are the same with those by this method, implying that the solutions of Gherkin approximation are identical with those of Litz's approximation. Now, Okay, thus we don't have to discuss the result again more here. Instead, we'd better compare collecting method with list method. List method representing bidirectional approach start from bidirectional principle. If there is no bidirectional principle, the bidirectional approach to approximation cannot be applied for the such problems. On the contrary, there is no limitation in front of Gallatin method representing the weighted list method. As a consequence, Gallatin method is more flexible than list method. In fact, the list method cannot be applied to most engineering problems, excluding solid mechanics. When this method can be applied to a specific problem, then Gallatin approach must be able to apply to it. It should be emphasized that the solutions are the same in this case. Now we are going to connect conceptually what we have understood for approximating the boundary problem with a finite method. For application sense, one of the difficult problems of the two approximate methods of boundary problems is how to generate automatically and effectively the basis functions for tri-functions. This simple example is sufficient enough to give us some ideas for solving the problem. We employ this function as the only one basis function. It is piecewise linear, and it should thus be formulated in this way. You know, its first derivative is step function. It is bounded, and thus the back scale integrable. However, the derivative of the step function is unbounded at x equals 1 over 2. So this function belongs to the first order Solar function space, the lowest order function, to meet the requirements imposed on the basis function. You remember that we already talked about the requirements which is aimed to make the major term in the functional meaningful. Yes, this is major term in this functional. Of course, this function meets perfectly the essential boundary conditions at both ends. Substituting this trial function into this functional, we obtain a one-dimensional quadratic function of C1. The necessary condition gives us C1 equals 7 over 192. This figure compares the approximation with the exact solution. And you can find that approximate solution at the middle point is exact. It's very interesting. This phenomenon is called superconvergence. Enjoy superconvergence. Even though these good characteristics of superconvergence cannot be guaranteed for all problems, this example, I think, is sufficient enough for us to expect something for practical application of this approach. Now I'm going to find some goodness we can earn by using this kind of simple basis or a trie function. And you know that the basis function at x equals 1 over 2 is unity. Therefore, C1 means the unknown function value at that point. This allows us to enjoy the freedom from the problem of preparing trial function considering the essential boundary conditions. This fact will be explained in more detail soon. Let's summarize our experiences of this example before moving from classical approximation to modern computer-based approximation, that is FEM. We employ the lowest order basis function, which belongs to the pth order Sobolev function space. In this case, p equal 1. We found that the superconvergence happened at the slope discontinuity point because the basis function value at this point equals 1. The unknown constant became the unknown function value itself. This fact is really important in terms of automation, that is computerization of generating the basis function and the feasible trie functions. In FEM, we employ these kind of functions as interpolation functions, which have the same meaning with basis function in classical approximations. Zeta will be replaced by function n2 and the known constant C1 by pi 2, following tradition in this field. To define this function flexibly, we will divide the solution domain into FE model defined by nodes denoted by just green number and elements denoted by circled green number in this figure. At a node, a function like this, that is, interpolation function, can be generated automatically. This work can be done by even simple computers in a systematic way, following the instructions of software. Of course, computers have no brain, really no brain. The subscript 2 in function n to x is a kind of address of the interpolation function, while that in phi 2 in the address, phi 2 is the address of nodal value. That is, phi 2 means nodal value of a known function at node 2. That is at this node, at this point. And therefore, this is 2 element and 3 nodes FE model, finite element model. And this is the expression of trie function in FEM. Of course, integration in FEM is carried out element by element. It should be done like this in the classical approximation method, depending on hand calculation. So now we connected the classical approximation method with modern finite method. Therefore, 2 methods stand on the same theoretical or mathematical backgrounds. Only left are techniques, sometimes called finite techniques. I would like to obtain an approximate solution of the same problem for an FEM slide. The solution domain is discretized into 3 identical elements, as can be seen here in finite model defined by 4 nodes and 3 elements. Then we can define 4 interpolation functions at 4 nodal points as depicted here. You know, interpolation function is sometimes called as shape function. That is basis function in classical approximation methods. Each interpolation function has unit value at its associated node and zeros at the other nodes. And it is piecewise linear. The linear combination of these 4 interpolation functions, that is addition of interpolation function nix multiplied by phi I, becomes the trie function as formulated here. Note that the phi I is the nodal value of the function we want to seek. Of course, some are known in essential boundary conditions. In this problem, phi I and phi 4 are known as zeros. This is the eventual tribe function which meets the essential boundary conditions at x equals 0 and 1. However, we'd better impose these boundary conditions just before solving finite element equations for generality. As you know, the procedure of obtaining FE solutions consists of integration for constructing finite element equations and solving them. It is very important to recognize the difference in integration between classical approximation and finite method. In the classical approximation methods, increase in number of basis functions increases the difficulty in conducting integration tremendously because we must integrate over the entire solution domain at once. To the contrary, in finite method, we can calculate the definite integral element by element. I have to emphasize that there are only two linear functions in this case on an element. Therefore, the difficulty in integration does not change with the number of interpolation functions. Element-wise integration is one of good major characteristics of FEM. Now, I think you begin to know why we call our approach as finite element method. I already emphasized that approximation of boundary value problem theoretically reduces the problem in infinite dimensional function space down to that in finite dimensional vector space. I believe that the term finite was derived from this concept of approximation and element from element-wise treatment scheme in constructing finite element equations. Finite and element themselves don't have any meaning when they are separated, but it has great meaning which innovates the engineering when they are combined. I admire the pioneering researchers who contributed to naming it because FEM involves the exact meaning of it, and those who don't know this concept I explained cannot know its meaning at all and should live with some curiosity. Now let's go back to the integration element by element. Here I introduce the result only and use them to explain the concept, not for details. The details will be explained in consecutive lectures. Integrating the functions in an element-wise way after inserting the 12 functions and applying some simple mathematical operations, we obtain element equation for each element as given here, here, here for element 3. Okay. It should be pointed out that the element equations themselves do not have any meaning before so-called assembling procedure is conducted. Before assembling them, let's check the meaning of element equation with help of this figure. You can see that the heat source term of 1 over x squared for each element was discretized and saved in the light term of each element equation, here and here and here. Now, the problem thus became graphically like this figure, that is one-dimensional load mass system. After each element equation is assembled like this, we must apply boundary conditions to reach this final destination here. These are called finite element equations. After all, differential equation was transformed into just a set of linear equations. From them, we can obtain the unknown nodal values. Of course, the nodal values meet the super convergence as can be seen in this figure. Now, let's expand our discussion on expectation made and had in the previous slide onto more practical level. In the previous slide, we studied the simplest FEM model for this problem. The solution domain is discretized into elements with nodes. At each node, we define only one piecewise linear interpolation function which has unit function value at the node and zeros at the other nodes. In this case, the unknown constant mean the nodal values of a known function. Thus, we became set-free from problem of preparing trial functions satisfying the essential boundary conditions. Now, I already said that the only difference between classical approximation method and current FEM lies in how to flexibly prepare the trial function. The secret of FEM lies in discretization and interpolation. There's, of course, a minor difference in expressing the functions and unknown constant as summarized here. But the major theories for approximation are the same. In this FEM model, we can generate three interpolation functions, but the right and left ones disappeared to meet the boundary conditions. Now, this work became very, very easy, regardless of geometric dimension. By hand calculation following FE procedure, we can find the FE solution like this. You better refer to the reference for more details. Okay, now you're allowed to add one node additionally. Please make up your mind for the best point. Here? Or there? Here? Yeah, if you want to add a node here, you might be very rich. It's okay. I think the point you here and the second choice around here. If you increase the number of nodes more and more, the solution will become better and better. So we don't call these predictions as approximate solutions, but we call FE solutions. They can be controlled in terms of accuracy. Okay, of course, without assistance of computers, this technique is useless. Anyway, nowadays computer calculates really fast, and this technique occupied the center of the engineering. However, it's just one of techniques. For becoming good engineers, you'd better proficient more and more at theories of mechanics.